What I'd like to discuss today are some of the ideas about where the future of computation might take us. And in particular, I'll touch upon these ideas of quantum computation and why we might actually want to pursue them as a viable way for continuing our technological progress. I'm grateful for support from the Center for Computing Research at Sandia National Laboratories. So to jump right to the end, what I'd like to discuss is a future of computing, a future built upon trapping atoms or ions in free space and shining laser light on them in order to do computation, or perhaps burying some superconducting devices at the bottom of Dewar jars, or perhaps even using particles of light themselves as ways of storing, transmitting, and doing computation on information. And the point being that we have all of these novel systems to compute on. We've invented them, we've designed them, we've engineered them to do all sorts of interesting things. But you might say, well, what advantage do they have over our bread and butter silicon-based systems? Why exactly would we want to think that we could build a computer out of these things? Well, I think to answer that question, we should go back to where we come from with respect to computing. And in particular, I'd like to emphasize that the miniaturization of technology is what has powered our technological and economic development as a society and as a nation. After World War II, we built monstrous, huge computers like the ENIAC or the UNIVAC. They were big, they were kind of slow, they had all these unreliable vacuum tubes, and you literally had to pick bugs out of the machine in order to make the thing work. This is undesirable because you're essentially, well, stuck with all of these very difficult electronics and unreliable physical parts. And it wasn't until a little while later, with the invention of the integrated circuit and the transistor, that we were able to make computation something that the average person could do. We invented desktops. That brought computation into our homes. We invented laptops. It brought computation to us on the go. The point here being that as we've made technology smaller and smaller, we've not only able to do more interesting things with it, but it also changes our relationship to that technology. And you really only have to look no further than the modern age in order to really appreciate this. Many of us carry around a smartphone in our pockets, literally just a miniature computer that has apps for fun and productivity and for keeping in contact with people. People wear smart watches, same thing as a smartphone just on your wrist, and a few of the more adventurous of us have pushed the frontiers of putting computation on things like our personal wearables. Google Glass is a good example of that. The idea of embedding electronics in our clothing is another. The point again that as this technology has gotten smaller, it's changed what we think we can do with it, and it's also changed our relationship to it. Now, why has this development been possible? Well, the canonical idea is something called Moore's law. And Gordon Moore observed at the beginning of the birth of the semiconductor industry that roughly every 18 months, twice as many transistors are put on each integrated circuit. So every year and a half, you get twice as many transistors. And this is important because transistors form the building blocks of our integrated circuits, which in turn form the building blocks for our CPUs and other processing devices. As a result, if you can put more transistors on a chip, you can get more computation out of it. And so I went to Wikipedia and looked up transistor counts for various chip architectures and whatnot, and when you plot them versus time, you see that the trend that Gordon observed in the early part of the semiconductor industry, well, it seems to have continued essentially unabated. For over 40-some years, we have doubled the number of transistors on our chips. And a natural question arises at this point. Where exactly does this miniaturization end? Clearly, you can't fit infinitely many transistors on a chip. So where do we stop? Well, one of the fundamental practical physical limitations of this, of Moore's law, is actually the feature sizes on the integrated circuits. So I've read that a typical feature size on an integrated circuit is something like 10 nanometers. In comparison, this is roughly on the order of 100 atoms, So the smallest features on today's integrated circuits are maybe 100 atoms or so. 100 atoms in size, I should say. And it's believed that we can get down to 5 nanometer and eventually 1 nanometer technology. Now, in comparison, the average human hair is something like 20 micrometers in diameter. Your average bacteria is something like 1 micrometer. And so the tiniest features on these integrated circuits are actually so small that it's pointless to put them in this presentation because we wouldn't be able to see them. What happens when feature sizes become that small are quantum mechanical effects become important. The laws of the very small world are different from the laws that you and I experience in the course of our day-to-day lives. Because of this, it's believed that essentially once you push past 1 nanometer technology, quantum mechanics will overwhelm your circuits and your chips, meaning they will become practically useless. So the question is it game over? Is there no way that we can move forward and try and make this work? And some of the work that I've been thinking about essentially says, well, why don't we put quantum mechanics to work? Namely, if Moore's law is ending primarily because quantum mechanical effects are kicking in, then instead of trying to fight them or find ways around them, let's embrace them. Let's build computers whose fundamental operating idea is that they rely on quantum mechanics. And because of this, these computers can do things that classical computers probably can't do very efficiently or very quickly. And they also give rise to a whole host of interesting engineering, computational complexity, and physics-related questions. So if you're an engineer, a quantum computer requires rethinking the architecture, design, and manufacture of computers. Why might this be the case? Well, today's computers rely on motherboards on which we put integrated circuits, other various chips, other various devices. A quantum computer could be something as simple, or complicated if you like, as trapping ions in free space using electromagnetic traps. And then in order to do computation, you actually shine laser light on these atoms to cause transitions in, say, their electronic energy levels. And we encode information in that electronic energy state of electrons. So computation as shining lasers on atoms is not something that we're used to thinking about. And so we'd have to ask, how exactly are we going to put all of these ions together? We're going to have to build new traps. We're going to have to think about quantum data buses that allow us to move the ions and the information around. Further, we want to scale these things up. And as you make quantum computers bigger and bigger, it becomes harder and harder to control them because quantum information is very fragile. And so there's a lot of really good work that has to be done in understanding from a practical engineering-oriented standpoint how we could make quantum computers feasible. If you're a computational complexity type person or a computer scientist, quantum computing provides some interesting ways of thinking about computational complexity. That is to say, quantum computers can speed up solving some problems, but probably not all of them. For instance, quantum computers are good at searching a list or factoring numbers. So we'll be able to build a quantum version of Google, perhaps, or steal your credit card information. But quantum computers are not very good at planning a road trip. For technically oriented listeners, essentially, quantum computers can probably solve many interesting problems, but they probably cannot efficiently solve so-called NP-complete problems. Further, if we have a quantum computer, then we can think of defining quantum computational complexity classes. That is, we can define the quantum analogs of P and NP and try to understand how exactly quantum computing is different from classical computing. And there's really a whole host of interesting questions that I really can't appreciate, but I hope that computer scientists will work on. Now, as a physicist, quantum computing is interesting primarily because the difficulty of simulating systems might actually tell us something about nature. What does that mean? Well, consider, for instance, the following problem. I have some molecules, and I want to put them together in order to make some new compound or some new metamaterial. And I have to understand how these molecules are going to arrange themselves as I bring them closer and closer together. And I want to be able to predict the electronic and other properties of this molecule, of this combined molecule, once everything binds together. Now, doing so on a classical computer, even a supercomputer, is a very difficult thing. And it's so difficult that for all practical purposes, in order to do something like the protein simulation on the left, you would really require a very, very long time to come up with some sort of energy configuration. And it was problems like this that got the physicist Richard Feynman thinking about quantum computing. And he said, well, hey, if I had a machine that operated fundamentally quantum mechanically, then there's probably some way I could simulate my complicated many-body physical system using this quantum simulator. And that's what's been pushing physicists to think about these things, is we want to be able to understand nature. And in order to understand nature, we might build these quantum simulators and then use these quantum simulators to learn something. What's really cool about this is that we could actually gain insight into how the universe works by building these little quantum simulators and seeing what they do. So in sum, what I presented was sort of an idea about how, as Moore's law kind of comes to an end, and we want to look beyond Moore in terms of computing, one way forward is that we could embrace quantum mechanics as an operating principle for our computers. And just as the emergence of the desktop and the laptop and Google Glass and smartphones from previous technologies have changed the way that we think about computing and changed the way that we use computers, so I also hope that one day we will add quantum computing to that list, because it will provide us with a new way of computing. Thank you.